Hello, I'm Craig Prunty, VP of Marketing for SiPearl. I'm glad to be here virtually at Lenaro Connect 2020. Today I'm going to talk to you about SiPearl and the European server processor. I'll give you an overview of SiPearl for those of you who don't know us and our value proposition, our target markets, key partnerships, and then I'll discuss the high-level architecture and design elements of our first generation Rhea processor and the common platform associated with our processors. We'll talk a little bit about ecosystem and then the software elements and where groups like Lenaro are making a difference. SiPearl was founded out of the European Processor Initiative to develop the European processor solution. Our headquarters are in Maison Lafitte, it's just west of Paris, with a second design center in Duisburg, Germany, near Dusseldorf. Our headcount, we were founded in 2019. Our first employee came on board in January 2020. We're now at 22 people and growing, coming from companies like Intel, like Atos, like Marvell, with good HPC and server processor experience. Our architecture is based on the ARM Neoverse Zeus cores, and we're targeting our first generation to go into the EU pilot machines as well as the HPC European exascale machines. Our value proposition can be summed up as P3S, so 4 elements: performance, security, safety, sovereignty. So first, performance. Our first generation high performance server processors designed on the ARM Neoverse Zeus cores, the Zeus NOC, and associated acceleration. EU sovereignty is important for us. We were founded through the EU Commission. We are developing for European customers, for European markets. Now we will sell outside of Europe, but our target in terms of development is the European market. The flexible common platform, the idea here is decoupling the design and scalability of the general purpose processor and accelerators while closely coupling the performance of the two. And we'll talk about that in later slides. And finally, safety, security, and data protection are key values of Europe and the European Commission. In terms of our target markets, they're very important for HPC, but even more so for the follow-on markets such as edge and automotive, and we'll be bringing innovation there. Our market strategy is tied to sovereignty. We'll target European markets and design for European customers. Our first market will be high performance computing with our Rhea processor, and we'll focus on time to market to ride the European exascale wave. Beyond that, then, cloud computing is growing in Europe, and the European Commission is pushing this forward with initiatives like Gaia X. The edge workloads quite often are similar to the cloud workloads with a different cut in software focusing on elements like lower latency and local processing capability. So overall, SiPearl covers the full range of advanced computing from high-end HPC to edge devices. The world of ARM HPC, so ecosystem being key here. A fully fleshed ecosystem allows you to build more systems. The more systems you have, the more you can do to develop your ecosystem. So folks here at Lenaro are not surprised to know that ARM is the most widely used ISA on the planet. Over 200 billion processors sold today. 200 billion. That's a lot of processors. If we look at the map here, the ARM world, obviously across the US, Europe, China, and Japan, we can start in Japan with the Fugaku system for HPC. This took all the top awards this year. The first ARM system, HPC system, to hit the top of the LINPACK scores, top of the HPCG, as well as the Green 500. In Europe, you have the Mont Blanc systems at CEA, as well as in the UK, the Catalyst systems and the Isambard system at GW4. And the US, Sandia Astra system, as well as the system at Stony Brook and other research systems are driving ecosystem development, application porting, and really growing the world of HPC. The EPI is an important partner for SiPearl. Actually, the EPI consortium has 26 important partners for SiPearl. I'm not going to spend a lot of time on this slide. Jean-Marc just gave a great 15-minute presentation ahead of mine describing the EPI, but I am going to summarize the goals of the EPI to tie them into this presentation. So obviously the development of a general purpose high performance processor, which SiPearl is bringing to market, high performance RISC-V based accelerators, computing a common platform for edge and autonomous cars, and also targeting other important markets in Europe, such as AI and big data. So the target is to take IP to product and EPI innovation into SiPearl end products. Now we're getting to the meat of the presentation. We'll talk a bit about Rhea, our hyperscale processor. Now this is a non-NDA presentation, so I can't go into great detail on our block diagrams or design elements. Sorry, our design specifications. But I will talk about some of the design elements that we're using, starting with the Zeus CPU core. And again, a very high performance CPU core connected to an intelligent memory subsystem and supporting, of course, the ARM ecosystem. This is connecting up through a coherent network on chip, a memory coherent network on chip, and it's topology aware, so we can scale this up, and that's important for us to be able to address multiple markets. Again, HPC, a very high performance market, a lot of cores, but some of our other markets requiring lower performance, so you want to be able to scale the chip, or even an HPC to either create multiple NUMA domains in a single chip or a single NUMA domain across multiple chips. And of course, ARM gives good isolation between the compute units, which is also important for our markets. Rounding out the memory subsystem, you see here high bandwidth memory for high bandwidth, of course, and then DDR for high capacity. And again, these all connecting through the network on chip, so having coherence between the memory domains. And finally, our high-speed interface, so PCIe Gen 5 as well as C6 links for coherent interfaces, and then a low power, low latency die-to-die interface to support our common platform, which we'll talk about in the following slides. Here we come to the common platform. This is an innovation coming out of the EPI. The idea is to separate the design of the general purpose processor and the accelerator to allow them to scale separately, but to closely couple the performance. This allows you to integrate the best-in-class processor cores, and you can innovate on the acceleration side. You can leverage industry IP and share that as appropriate across the two technologies. And you'll be able to leverage the foundry and manufacturing technologies that make sense for each element. We'll talk about this more in the next slide. So here we have a representative diagram of the common platform. Now, this is not an actual diagram. This is just representative to show the different ways that we can connect up the accelerators to the general purpose processors. So traditionally, you have the accelerator connected over a PCI Express interface as shown at the top here, and that would be either on the motherboard or on an adapter card, maybe even over a network. More and more you're seeing connections over coherent interfaces. Here we show C6, could be in the future CXL or some other coherent interface. And this gives a more closely coupled performance because it's memory coherent. We are developing a die-to-die interface. We plan to make this an open standard, so anybody can design on this die-to-die interface. Now the advantage of this is you can put then a chiplet in package. That chiplet, again, it's decoupled in the design. It can be in different geometries. You can scale the size as you wish. You can also take advantage of IPs sitting in the general purpose platform. By using a high-speed die-to-die interface, you can avoid putting interfaces in your accelerator chip or memory in your accelerator chip, and you can take advantage of that over the low latency, high bandwidth die-to-die interconnect to use those IPs in the general purpose processor. This can save you on development time to market, and development costs overall, IP costs. In terms of a design goal, we're focusing on a balanced high-performance processor. When we say balance, we're talking about calculation performance versus memory bandwidth. And for HPC, this is an important measurement. Traditionally in HPC, you have very high performance processors with poor memory bandwidth. This is good for LINPACK scores, but it's usually bad for most workloads you want to run. So the goal is to have a lot of performance, but also a good balance between your memory bandwidth. And this is where the use of HBM as well as in-chip, in-core acceleration, the combination of the two gives you high performance, but also high memory bandwidth. Typically, HPC systems architected today, especially to get to exascale, most experts believe you're going to need both accelerators and general purpose processors. So the accelerator will give you that flop engine to get the high LINPACK score or high flop count, floating point operations count. So in a system, getting codes to run on a GPU or any kind of accelerator takes a lot of work and optimization. So the number of codes that actually run on a GPU is very limited. Most of the codes rely on the general purpose portion of the system to get the job done. And this is where, again, having the high flop count, that gets you the LINPACK score, gets you to exascale. Having a good, well-balanced general purpose processor, that gets you a good working HPC system for the majority of your actual workloads and customers. Ecosystem. So this is one of the most important slides in the deck, but probably needs not that much talking from me. The folks at Lenaro, I'm sure, understand the importance of ecosystem. So good hardware without software is a very expensive paperweight or doorstop. So here you see a lot of logos. This is representative. It's not everybody in the ARM partner universe, but each one of these is a brick that had to be shaped and set over time to grow the ecosystem for ARM. If you consider Calxeda to be the first ARM server company that founded in 2008, then this has been at least 12 years in the making to get this ecosystem in place, which I think it became self-sustainable a couple years ago where it was growing organically. We didn't have to go and push things to get done. We had people coming to us and saying, hey, I ported my code, port it easy. I'm tuning it now, but the port was super easy. Or my tool chain, I bought a server, I ported over my tool chain, it's running now. Can you help me understand a little bit about these performance elements? So the ecosystem now is a key element for ARM, and it makes ARM a real viable server processor alternative. Our final slide is showing the HPC software stack for ARM, which is another way of saying the software ecosystem. So I get asked a couple of times a month why we're not designing server processors on RISC-V cores. Why are we using ARM cores? And the answer is, of course, ecosystem. The color coding on this slide, it goes from red to dark blue, light red to dark blue, and this is designed to show the red is where we're showing spending more time and effort as it scales on things like library support or language compiler support takes a bit of effort on our part, then going to the dark blue where it's mostly the end users or partners and we support them. So thanks to the folks at Lenaro and other organizations developing this software ecosystem, the entire ecosystem, this has made a big difference in terms of bringing ARM server processors to market. Please continue helping with this. This concludes our keynote. You can contact SiPearl, the contact information here. We appreciate the opportunity to speak here at Lenaro Connect, and we hope to speak with you soon.